Hello. So in this short video, I will discuss microscopic error of time from multiscale perspective, an article which appeared recently in EPL. So microscopic laws, that is forces and equations, are time reversal symmetric. For example, uh, a pendulum which is acted by gravity, the equation of motion is symmetric under forward time and backward time. So forward trajectory and time reversal trajectories overlap. So the one going from the left to right is same as time reversal trajectory which will go from right to left. It turns out for this simple system, forward and backward motion are equally likely. However, at the macroscopic level, uh, things are asymmetric in time. That is, for example, uh, a kid was born, uh, that kid grows to be a young man, then at some point death comes. And it cannot be reversed. Similarly, events, for example, earthquakes happen and they destroy things and we can't undo it. So what is the cause for it? And it turns out is in macroscopic world, things are not time reversal symmetric. Because of open systems, forcing, and many factors. That's what this article is about. So let's take a slightly more complicated example, but which is still an isolated system. So microscopic laws typically focus on idealized things like point particles, isolated system, but we'll just consider springs connected together, many of them, uh, which is isolated. So energy is conserved in this system. Now this Fermi-Pasta-Ulam Stringo problem. Now for weak nonlinearity, the system is quasi-periodic. It has been shown numerically. However, for strong nonlinearity, the system shows randomness or it gets thermalized. That means energy is um, random or equally distributed, and it turns out the system does not go back to the original state. For large enough systems, uh, the time reversal time, if at all, which is called Poincare recurrence time, is too large. Anyway, so this system, which is isolated with many degrees of freedom, is time reversal. It shows asymmetry because of large degrees of freedom, nonlinearity, sensitive to initial condition. But in this article, we discuss open systems and other macroscopic phenomena. So, just to just to give the old the generic arrow of time prescription, which is the time flows in the direction of increasing entropy. For example, a gas confined in the left half of this box will spread to the full box once the gate is open, and this doesn't reverse. It's similar to the spring system where uh, the system basically spreads out. The reversal time, if at all, is very large. So we get from order to disorder, or less order to more, less disorder to more disorder. So this is the direction of time. The time flows in the direction where entropy increases. But there are systems where entropy is not very well defined. The Boltzmann entropy, for example, earthquakes or turbulence or human body. So for such systems, it was proposed that we can use energy transfers. So in generic macroscopic systems like earthquakes or turbulence or the Earth atmosphere, these systems are forced at large scales. It could be sun or turbulence. We have stirring by the external force, and this stirring gives energy at large scales, and that energy flows to small scales where it dissipates. So this process is irreversible. The energy does not flow back from the microscopic to macroscopic. And we don't have entropy, but we can use this energy transfer to define the arrow of time. Always flows from, in 3D, flows energy, the time flows in the direction where energy transfer takes place from large scale to small scales. We can make this system, this phenomena more general or more complicated by including the effect of environment in a more general way. For example, a combusting gas, or here the coal is burning, and this system is interacting with with the environment, and this gas is transferring heat, particles, sound waves to the environment, and this is not reversible. We can't bring back the sound waves or the particles. It's an open system, and uh, most of the world is this. It's not an isolated system, um, and most systems in the world are not isolated, including human body is interacting with the environment. The another system, which is another cause, not highlighted enough, is causality. So, dynamite ignition, which is the cause, leads to explosion, which is an effect. Now, so a cause leads to effect. Now, this is not reversible. When explosion, these things do not come back, and uh, then ignition is stopped. This doesn't happen. So, this cause and effect has a direction of time. First cause, then effect. And this also involves some subjectivity. Uh, that means the subject is important, who is igniting the dynamite. In any case, so this article emphasizes on the fact that the fundamental laws have idealized constructs like point particles and isolated objects. It turns out the results based on such idealized assumptions are normally not generalizable to macroscopic world. Macroscopic worlds have more complex interaction with the surrounding, with forcing, with dissipation, and these are what lead to macroscopic arrow of time. Thank you.